Hello, this is Nick, and today I will be talking about systems of differential equations and using linear algebra to formalize definitions and solve problems. So the overview of this, we will first of all be covering uh, exactly what is a differential equation, general form of solutions and things that we would use to solve these equations. Then we'll be doing a review of linear algebra, followed by the usefulness of systems of differential equations and the basic construction of a system. Then we will also be talking after that about homogeneous systems of differential equations, and finally a recap of further topics if people want to explore this topic more. So let's dive right in. So a differential equation is a type of equation which contains a derivative. So the rate of change is embedded within the equation, and we want to solve for the function that the derivative is being taken of. So solving this equation will give you a general solution, which is the solution to the initial equation. So if we plug in our equation right here, such as like y equals, I don't know, t squared, then there's some differential equation out there to where this would be the solution to it. So some examples of differential equations would be this one right here, which could be solved by separation of variables, which we're not getting into, but this is one. There's one right here which contains a second derivative, so we call this second order. And then there's one right here, which is a system of differential equations, which uses which expresses our derivative as a column vector. We have a coefficient matrix right here multiplied by a solution vector right here. So as far as general forms of basic differential equations, it's very effective to think about what exactly would make a good solution. So if we think about the equation e to the x, this is a natural choice for many differential equations because the derivative e to the x is itself. So for e to the x, it would satisfy this equation right here, because when we take the derivative and we plug, so we call this y equals e to the x, and you plug this in, we'd actually get this right here, which is really cool. So when we solve these, we also add a constant of proportionality, because adding a constant in front, no matter what value you choose, will always still satisfy the original equation. So now moving on to systems of differential equations for a second, our general solutions will be of this form right here. Now, our C1 and C2 are constants of proportionality, which are what we had up here, just arbitrary constants. Our V1 and V2 are the eigenvectors of the matrix A, and then lambda 1 and lambda 2 are eigenvalues of our matrix A. And that will make more sense later on. So now we are going to talk about some basic linear algebra, which will be very useful to us. So first of all, we will review the concept of the determinant. So the determinant of a matrix A, where these are generalized coefficients A11, A12, A21, and A22, this is equal to the product of these two, A1, A11, and A22, minus A21 times A12. And this is for a 2 by 2 matrix. So if you can see this right here, it'll give us this. And as long as these are only coefficients, we will always get a constant back. Now, our eigenvalues are denoted by this symbol right here, lambda, which will obey the following proportionality or equality, which is ax equals lambda times x. Now, if we remember that this equation right here, a times x, is actually a linear transformation, then what this is saying is that we can replace this with b, and our b is equal to b is equal to lambda times x. So what this is saying is that when you multiply a matrix A times a vector x, you will get another vector, normally b, which is only scaled by this proportionality constant right here, lambda, called an eigenvalue. So linear transformations, most of the time they scale vectors and they also rotate vectors. An eigenvalue only scales the vector which is being acted upon. So this vector right here is a multiple of this vector, which is very cool. And we find solutions, lambda, to this equation by using the characteristic equation, which we will talk about, which stems from the invertible matrix theorem. So now talking about the invertible matrix theorem, this says that A is an invertible matrix such that A is an invertible matrix, and this is equivalent to saying that AX equals 0 has only the trivial solution, which is X equals 0, 0. Now, if we also keep in mind that if the determinant of A is equal to 0, then the inverse of A is not defined, because from this, the inverse of A is equal to 1 over the determinant of A times this. If the determinant is equal to A, or the determinant is equal to 0, sorry, then this is 1 over 0, which is obviously undefined. So to find these eigenvalues, we use this equation, the determinant of A minus lambda I equals 0, and we solve this for lambda, because solving this for lambda will give us non-trivial solutions by this part right here. So AX equals 0 has only the trivial solution if A is invertible. And we want this determinant to be equal to 0, so not invertible. So we have unique solutions, X. And keep in mind that I equals the identity matrix, and lambda I is equal to lambda across the diagonals. All right. And then finally, we will be talking about eigenvectors. So we denote these by v1 and v2 for a 2 by 2, and we use a simple v. And the main equation governing this is A times lambda I times v is equal to 0. Now, keep in mind that each eigenvector corresponds to a given eigenvalue. So if you have an eigenvalue equal to 2, then that will produce a different eigenvector than a eigenvalue equal to 4, for instance. So now we are interested in finding the eigenvectors. Sorry, let's just say eigenvectors by the invertible matrix theorem. So we are looking for a vector x right here, which satisfies this inequality. So first we find our eigenvalues right here, and then we use this equation to solve for v, which will give us our eigenvector. What we do is that we take our matrix A, and then we plug in our given eigenvalue in right here, and then we perform row operations on this to obtain v1 and v2 for this right here. So our eigenvector here is actually a vector of 2 components. And so it makes sense whenever we do an example. So now moving on to the meat of this, we have systems of differential equations. Just getting some water really quickly. Ooh. So systems of differential equations are expressed with matrices. So if we have these two equations right here, dx dt is equal to 2x plus 4y, and dy dt is equal to 7x plus 2y, then we can actually represent, first of all, this derivative expression right here as a column vector of derivatives. There's a dx dt with a little arrow over it. And then we could write this right here as a coefficient matrix times the column vector xy. And when multiplying this out, we get dx dt is equal to 2 times x plus 4 times y, which satisfies this. And dy dt is equal to 7 times x plus 2 times y, which satisfies this. Now, we call this a homogeneous system of differential equations because in general, we have more added on to this right here. So, for example, if we take the same example, but we have this, see this right here, this is a column vector of like functions. And this would make the system non-homogeneous because when the system is homogeneous, then this part is equal to 0, and we're just left with this right here. So we use system of differential equations to describe the changing natures of things where there is multiple things changing at the same time. This could be anything from like weather patterns to fluid flow and tank problems, forces problems, and stuff relating to that. And a very classic example, which I love to talk about a lot, is the mass spring system. So if we have right here, we have two boundary layers, or two boundary walls, and we have springs with spring constants K1, K2, K3, and two masses in between these springs, M1 and M2. Then if we apply some force to this mass, let's say to mass 1, then both of these will start to move along with the springs, and the motion of each one of these masses will be different because the force is applied to this one, not to this one. So if we want to describe the nature of this, or like how the masses move with respect to time, we need differential equations to model the motions of each one of these masses separately. So going back to how to solve these systems actually. So earlier on in this video, we assumed a form of this using the exponential, which is a natural choice for differential equations. C1 and C2 are constants. V1 and V2 are eigenvectors, and lambda 1 and lambda 2 are eigenvalues. So our homogeneous system, again, as a period, will always be in this form, but we will be assuming right now that we will be dealing with a coefficient matrix only, not a matrix with any variables in it. Hopefully that makes sense, and now we will move on to a basic example. All right, so now we'll be doing an example. So let me just write this down, example. And we'll be solving today the equation dx dt is equal to 3, 2, negative 2, x. So how would we go about solving this? So first of all, if you remember from over here, we just need our eigenvalues and our eigenvectors. So let's find the eigenvalues first. So we use this equation that a minus lambda I is equal to 0. And then we just plug in a, and with I being the identity matrix, we get that 3, 2, negative 2, minus lambda, there. And because this is the identity, it's just lambda multiplied by the ones on the diagonals. And this gives us determinants 3 minus lambda, 2 minus 0 is 2, negative 2 minus 0 equals 2, and then negative 2 minus lambda. And then this gives us, by this times this, which is 3 minus lambda, and then times negative 2 minus lambda, then minus 2 times negative 2. All this is equal to 0, and when multiplying this out, we get negative 6 minus 3 lambda plus 2 lambda plus lambda squared plus 4. And then this is going to be equal to lambda squared minus lambda minus 2 is equal to 0. Now, we can solve this by the quadratic formula. This is a 1 in front of it. Our constant right here is a negative 1. That's a 2, so we get, first of all, negative b plus or minus b squared minus 4ac divided by 2a. And then for this we get negative b is just 1 plus or minus b squared is negative 1 squared, not plus, minus 4a is 1, and then c equals negative 2. And then 2 times a is just 2 times 1. And what we get here is we get 1 plus or minus 9 over 2, just 1 plus or minus 3 divided by 2. And this gives us lambda 1 and lambda 2, which is equal to 2 or negative 1. So right here we have our eigenvalues. Now we need to find the corresponding eigenvectors. Doing this, we will use the equation a minus lambda I v is equal to 0, and we plug in our corresponding eigenvalues. So for the first one, 2, we have for lambda 1 equals 2, we have copy down a again, negative 2, minus the identity times 2, so that's 2 on the diagonals. And then this gives us, not 3, sorry, 1, negative 2, 2, and negative 4. And then all this is multiplied by v, our eigenvector, that's equal to 0. And now we can just do row operations to reduce this. But here, actually, we can note that row 2 is actually just 2 times row 1. So we can cross that out and forget about that. So we actually get the equality by multiplying this out. If we remember that v is equal to v1 times v2, we get, by matrix multiplication, 1 times v1 is equal to v1, negative 2 times v2 is equal to minus v2 equal to 0, and v1 is equal to 2 v2. So if we let v2 equal 1, then v1 will be 2 times 1, which is just 2. So putting this into our spots right here, we get, so our eigenvector 1 is equal to 2, 1. And now we will do the exact same procedure for eigenvector 2. So similarly, copying a again, you guys know the drill. Since it's negative 1, we'll do add or addition. Then that will just give us 3 plus 1, 4, negative 2, 2, negative 2 plus 1 is negative 1, and times v equals 0. Now if we notice that row 1 is 2 times row 2, then again we can just cross the bigger row out, say that, and we are left with 2 times v1 minus v2 is equal to 0, or 2v1 is equal to v2. So if v1 is equal to 1, then v2 will be equal to 2. So plugging these back in for our v2, we get that v1 will be equal to 1, and then v2 will be equal to 2. So compiling our information, we have eigenvector 1 their eigenvalue 1 equals 2, eigenvalue 2 is equal to -1, and eigenvector 1 is right here, 2, 1, and eigenvector 2 is equal to 1, 2. And now, plugging all of this back in for our general system, I'll leave this right here, we get, and we're going to write this in terms of just x of t. X of t is equal to our constant c1 times eigenvector 1, which is 2 times 1, and then e to the lambda 1, which is e to the 2t, and then by the principle of superposition, we add these two together and we get this plus c2 eigenvector 2, 1, 2, e to the -1, so e to the -t. And this is our solution to this homogeneous system. Sweet. Now, the last thing I want to cover is just where we'll be going from here. So we'll be talking about further applications. Further applications and topics, actually. So piggybacking on this, what people would normally do after this is that they would cover repeated eigenvalues where both the eigenvalues are equal. So we use a generalized eigenvector to solve systems where lambda 1 equals lambda 2. Next, we can also solve systems in the form dx dt is equal to ax, which is what we had, but plus our non-homogeneous term g of t. So we can solve those. Next is that we can also solve, oh, by the way, we solve this by using another topic in linear algebra using diagonalization, which is very cool. We can also solve equations that have complex valued eigenvalues. We can talk about this awesome thing, which is used in a little bit higher level stuff, the matrix exponential, which is exp at, or e to the at, where a is a matrix. And then finally, two other things. We can use these in numerical methods, as well as analyzing stability of solutions and analyzing autonomous systems. And that should be it. Hopefully you guys have learned a whole lot about this, and this is a ton of fun to make. And yeah, this is it. Hopefully you guys have a good day, and thank you for watching. Bye.